Did ancient builders in quake-prone regions develop sophisticated seismic-resistant techniques? Were their techniques lost to history, or were they so advanced that we're just now recognizing them? Let's look at the evidence. Yes, in several quake-prone regions, builders developed surprisingly sophisticated and empirically seismic-resilient techniques. They didn't have modern seismology or codes, but long experience with earthquakes led to design choices that align with today's earthquake engineering principles. Highlights by region. First, the Andes. Inca builders in Peru and their predecessors in the area developed precise, mortarless ashlar with multifaceted interlocking stones that can rock and reseated without collapsing. Walls lean inward, helping resist overturning. They used trapezoidal doors and windows to avoid overstressing corners and generous wall thickness to avoid brittle fractures. Rounded or bossed stone faces avoid stress concentrations. Through stones tie wall faces together. Tight joints and well-drained, stepped terraces and foundations avoid hydrostatic uplift and liquefaction. In Cusco, Inca walls like those at Coricancia foundations and have repeatedly outperformed later colonial masonry in major quakes in 1650 and 1950, even earlier. Tiwanaku builders used metal cramps and dovetail clamps between stone blocks. Connections like these help resist shaking. Further east in the Aegean and Greco-Roman world, some Minoan and Mycenaean sites show timber lacing embedded in masonry, essentially horizontal wooden bands that add ductility and tie walls together. Greeks and Romans used iron or bronze clamps and dowels set in lead between blocks. The lead cushions and spreads loads, improving tolerance to movement. Roman concrete with lightweight aggregates and extensive use of arches, vaults and coffer domes reduced mass and created redundancy, beneficial in quakes. However, many classical temples remained vulnerable. So while some details improved performance, seismic design wasn't systematic. In East Asia, traditions like those in China and Japan developed timber post and beam frames with mortise tenon joinery and bracket sets or dugong that allow components to rock, slide and dissipate energy. Multi-story pagodas like the Yingxian wooden pagoda, or Japanese 5-story pagodas with or without a central shimbashira, have survived numerous earthquakes. Tests show that bracket sets and friction damping are key. Also note that light superstructures reduce seismic inertia compared to heavy unreinforced masonry. In the Himalayas and West Asia, related traditions developed timber-laced masonry systems like Doji Dewari and Tak. These use continuous wood bands at sill lintel and roof levels and flexible infill. These systems have shown consistently good performance in recent quakes, illustrating an old but empirically tuned idea. Finally, in Egypt and Mesopotamia, there's less explicit evidence for anti-seismic intent. Massive low-rise forms, wide bases, and excellent foundations and leveling helped stability. But many areas were less seismically active than the Andes or Japan. So, what does advance look like? It means ductility over brittleness, wood lacing, bracketed timber frames, lead-set clamps and interlocking stone all allow controlled movement without sudden failure. Good connections and tying prevent walls from separating. Geometry that resists overturning includes batter walls, trapezoidal openings, regular plans and redundancy. Also, reduced mass and good foundations lower forces and prevent foundation failure. Debates and myths. First, base isolation. There's no solid evidence of true ancient roller slider isolation systems. Some lead pads, sand layers or bedding details reduce stress and help leveling, but are not modern isolation bearings. Second, intent versus outcome. In many cases we infer seismic intent from performance and recurring details, but explicit written design rationales are rare. Bottom line, several ancient civilizations built demonstrably resilient structures, most clearly the Inca and timber building traditions of East Asia, whose solutions were empirical but often align with modern seismic principles. If you want, we can dive deeper into one tradition or compare a specific site's details to modern code concepts.